Good morning. I'm Dave Okar, Vice President of Aerospace Sales with Bodycoat. And I've got about 30 years experience in the heat treating and brazing market and 20 years as an ITA member. And wanted to thank Jennifer and her team for letting the panel speak today in Dublin on additive. And we'll jump right into it. So I'm going to be talking about the value add portion on how it pertains to additive services. So a little bit about Bodycoat at a glance. We are the world's largest and leading service provider. We're split into two business units: classical heat treatments and specialty technologies. 165 plants around the globe, 22 countries. We service aerospace, energy, automotive, general industrial. 4,700 employees to support you. We're a service provider. We don't manufacture anything, so we're like a dry cleaner for additive or any metal parts. You drop them off, we service them, we send them back. OEMs, tier 1, tier 2, tier 3, mom and pops, it doesn't matter to us. We're just happy to process your material. So additive, this might be a little beginner for some folks, but additive, over the last 10, 20 years has really blown up. We never used to consider traditional machining as subtractive. So now that we're into the additive world, some of the benefits of it are greater design freedom compared to the conventional casting and machining, lightweighting, designing parts so that material is applied only where it's really needed. Buy to fly ratios, you got to think about that when you're thinking of airplanes. Combining parts into one, including new functions such as complex channels, that's eliminating brazing, possibly EB welding, friction stir welding, processes like that. Net shape process helps reduce raw material use and compared to machining. So typical alloys used in the additive world: aluminum, titanium, cobalt chrome, more aging steel, nickel, steels, and copper. And all of this material needs to be, you need to do post-processing before you can put it on an airplane, put it in a body and whatnot. So adding value to additive manufacturing. So Bodycoat provides a complete service solution for metals built by additive manufacturing, including stress relief to minimize distortion, residual stress. We can EDM to prepare the component for hot isostatic pressing, also known as hipping, heat treatment and hip to remove microporosity, and associated quality assurance testing. If you look on your left there, that's a typical build plate, some nozzles. So the value add is a reduction in rejection rates and inspection costs. Fatigue properties are on par with raw material. Significant improvement in fatigue strength, fracture toughness, and tensile ductility. 100% reduction in porosity is possible, and improved machine surfaces with consistency and properties. So the process, if you take your metal additive manufacturing, it really boils down to two things: blown powder technology, DED or LMD, and then powder bed. Most of the stuff we see is typically powder bed technology, which can be broken out into electron beam melting or EBM, laser beam melting, LBM, or inkjet binder technology. So the value add portion, how do you get from the CAD design to an airplane? So you've got your CAD model, you've got your powders, grades, then you build your plate, then the value add comes in your heat treatment. So, your first step is going to be a stress relieve. Then you'll roll it into a hip for hot isostatic pressing, which will get rid of the porosity. Heat treatment to improve the microstructural properties. You wire EDM the part off the build plate. The build plates are reusable. Do material lab, metallurgical analysis, and your parts are generally good to go on an aircraft. So hipping, don't know how familiar you guys are with that. That's an absolutely necessary process. So turbine blades and vanes from the high temperature section of jet engines are routinely hipped to ensure freedom from microporosity. HIP is used to optimize the properties of the latest generations of single crystal and directional solidified investment cast blades. So Bodycoat can work with cost-effective development of metals using HIP technology. And a few of our processes are trademarks. So Densol is aluminum densification. Not many people can do that. We can do that. Densification of superalloys and titanium castings. Powder met manufacture of complex net and near net shaped powder metallurgy components to novel materials. So powder met, we'll take it, we'll put it in a can, we'll hip it, and you'll have a near net part. Hip brazing and hip cladding. So if you're not familiar with a hip vessel, if you look to the left, it's generally a very tall cylinder. The part in the middle is your can. You load your parts in there. We can run up to temperatures of 2000 C with isostatically applied gas pressure up to 45,000 PSI, so very high pressure. It's used to eliminate porosity in castings and consolidate powder metallurgy materials into fully dense components. Dissimilar metals can be bonded together to manufacture unique, cost-effective parts. Bodycoat operates a global network with over 50 hip vessels across the globe to help wherever the customer is printing. There's two major hip routes for customers. There's product fab, which is we'll pour the powders into the can, and then there's your standard hip porosity removal through hip densification. On any given week, we're processing tons of materials, aluminum, steel, cobalt, titanium, nickel-based superalloys, and all of that is to reduce the porosity. So build plate removal and other value add. So the parts are generally built up on a plate, and we have an alternative to standard EDM machine or bandsaw to cut the parts from the build plate. You maintain part integrity by ensuring the parts are undamaged during the cutting process. You can separate laser powder bed fusion from large build plates up to 500 kilograms. The typical build plate when Additive came out was about 350 millimeters. They've grown significantly over time, and build plates are checked, serviced, and can be used again and again up until you exceed your part thickness of the build plate. So component journey. Here's a typical part. You've got your 3D printed part. After that, the plate, you've got to build up. It'll come over for a stress relieve, typically in vacuum. After that, the part will be EDM'd. It travels over to a hip for densification, back to a vacuum furnace to get your mechanical properties, off to a test house. After testing, maybe a final machine, and onto an engine blade somewhere on an aircraft, or from a medical standpoint, same thing, your hip, your elbows, and whatnot. So Bodycoat Additive Centers. Aerospace and defense, we're on commercial jet, space, military aircraft, armory and munitions, automotive, a lot of motorsports, cars and light trucks, motorbikes, heavy trucks, GI, general industrial, medical, food and beverage, tooling and mining and energy, stationary turbines, nuclear, oil and gas, and renewables. Our biggest market right now is the aerospace and defense. Energy's quickly catching up, and space is a big one, just because you can scale up for space a lot easier than you can high production. So Bodycoat's Additive Centers of Excellence in the States. Greenville, South Carolina is a full service model, vertically integrated with hip production and vacuum. Cincinnati, product development, vacuum and aluminum, and then Berlin in New York is vacuum and aluminum. So over here in Europe, we've got 8 standard heat treat locations throughout the UK, and our additive centers are in Shard and Derby, with our hip centers in Chesterfield. We've got a little typo there, we're missing an R. So for the local guys on this side of the pond, quite a network to support you. Bodycoat, we like to be your partner of choice for additive. The world's leading and only global provider of thermal processing services. International network, 165 facilities across the globe. We support our customers' ability to produce superior components. As customers' business expands, Bodycoat with our global footprint can support you throughout the US, Europe, Asia. Quality accredited facilities, NADCAP, AS 9100, AS, you name it, we hold the approval. Expertise in thermal processing, hipping, hot isostatic processing, and surface technology. And we are committed to reducing carbon emissions, investing in lower emission technology. So we like to take the heat treat away from you guys. Of course, it benefits us, but it helps with the carbon footprint. And we're supported with 4,700 employees, a lot of PhDs, metallurgists on staff to support your AM needs. That's a quick overview for the value add portion. I'd like to introduce our next speaker, Dr. Alexander Clausen, Vice President, Additive Manufacturing for ALD Vacuum Technologies. He will be speaking on advanced vacuum furnaces for metal powder production and additive manufacturing, bridging raw materials and products.
Yeah, thank you. Happy to be here and have the opportunity to having a talk today. The topic I want to touch upon is only a small portion of what we at ALD Vacuum Technology are busy with. It basically embraces the part of the production chain that brings you from a raw prefabricated material like an ingot or a rod to a metallic powder to then a 3D fabricated part in a near net shape form. This basically pinpoints the content of my talk. Just a few words on AMG or ALD. On ALD, this is basically my company, and on AMG, it's the parent company where ALD Vacuum Technologies is incorporated. Then the two production systems for powder bed production and for additive manufacturing. And finally, I'll give you a quite uncommon application example on how to use additive manufacturing for recycling purposes. A few words on AMG. This is the parent company of ALD. The two first main business segments are AMG lithium and AMG vanadium, so producing specialty materials, stretching out from mining activities to the processing of raw materials and pre-products. And this is accompanied by a third business segment. It's the AMG Technologies, where we have all the machinery to process these materials. So one of those companies in the AMG Technologies is ALD. We are located near Frankfurt in Germany and have roughly about 900 employees. Our products are mainly in the segments of metallurgy and heat treatment. And the next slide, I'll show you the products that we offer. And we offer also services to automation, after sales, melting services, and heat treatment services. This is just a brief overview of the machinery that we offer. We have systems for casting, for melting, and remelting and refining, but also for heat treatment, coating, and even powder atomization. And I will today focus on one of the systems that's shown here. It's a powder atomizer, and one very new system that didn't even make it to this overview. It's an additive manufacturing machine. The process chain that I want to focus on is, well, it starts at a raw material, so some sort of raw material. It's a prefabricated rods or ingots that are fed into a powder atomizer to produce metallic powder. And this powder can be used for various applications, amongst others, additive manufacturing. So these are the two production systems. I picked an IGA system. I will show you later what it is and how it works. Of course, you can produce powder in various different ways. So naturally, the powder that comes out of an Eiger system cannot only be used for additive manufacturing using a powder bed, but it can also be used for metal injection molding and other processes. And on the other hand, our additive manufacturing system cannot only utilize powder from an Eiger system. The powder can come from different sources. It will become clear during the course of my presentation why I picked those two systems. So first, an Eiger system for powder production. Where are the benefits of this system? The action takes place up there where the melting chamber is and the nozzle is located. Down there you have the atomization tower where the molten powder falls in, and the collection system and sieving systems. The benefits of this system is that you atomize without having a contact to a mold or a die. So you can produce powder that is prone to take other materials like ceramic particles or the like, and have a high purity of your material. So it's very much advantages for reactive materials like titanium in this case, or also for refractory metals. The raw material or the pre-processed material is an electrode feedstock. Here it's just a rod with a conical tip. This is introduced into a induction coil that then heats up the rod, and the melt stream that forms at the tip of the rod falls down and free fall through a nozzle without having contact to any other elements of the machine, and is then gas atomized using a inert gas stream. Basically, we have two different Eiger systems. The standard system, which operates with hardly any overpressure in the melt chamber above, but then uses a high amount of inert gas for atomization. Here we can reach D50 values of 60 to 150 microns. So it can be set specifically where it is needed. The second system is pretty new. It's an Eiger Premium with a modified nozzle system. It has a pressurized melt chamber with up to 25 bar, and for that a very much reduced specific gas consumption, which lowers again the carbon footprint. The D50 values reachable are between 20 to 80 microns. So we have a shifted range of particle sizes that are achievable with this system. Just to give you an example, this particle size distribution was produced for selective laser melting, so powder bed fusion process using a laser beam. And the blue curve shows the standard Eiger system, and the green curve shows the Eiger Premium. So with the standard system, we can achieve a yield of about 40% that is usable for selective laser melting. The rest is out of spec, so either fines or too coarse powder. And within Eiger Premium, we are now able to shift this now to increase this number to over 60%. And this can be set for different processes. So if you want to have metal injection molding powder, you can modify the process to give you a different particle size distribution. Now, what can we do with the powder? Can do various things, amongst others, put it into an additive manufacturing machine. Just to recap how this process works, We have different variations. For example, this is one with 3 compartments where on the left-hand side and the right-hand side, you have the power supply coming from below. And in the middle is the operational area of the electron beam, where you can achieve, where you can interact, where the electron beam can interact with the powder bed. So this is where the action takes place. And the steps involved are powder application, then heating up the powder to a certain temperature, depends on the material at hand. We are usually in the range between 600, 700 degrees C operation temperature to up to 1,200 degrees for titanium aluminides. And the electron beam has 3 tasks. The first task is to preheat the powder. The second task is to melt the powder in locations where it is needed. And the third one is optional. You can do monitoring. So you can use the electron beam like like an SEM, so a scanning electron microscope, just for monitoring reasons, to detect any defects like pores or other faults. And the machine we built looks like that. So what you just saw a slide earlier can be found here in the power application system. So here we have the 3 compartments for the power supply, and in the middle sits the build chamber. The power application system is outside the machine just for maintenance reasons. It usually sits inside the vacuum chamber, which is located in the center. And this guy is Robert. He has almost the same size than me, just to give you an idea how big this machine is. We created this machine with 3 main goals: to have to be able to produce large parts, larger than what is found on the market, and with very high build rates. And also use the unique features of the electron beam, like I said, for the monitoring, and a better interaction with certain powder materials where laser beams are having trouble. This is just to give you an idea about the moving directions. This is just for maintenance reasons. You can remove the power supply from the machine. But the more exciting one is this one, where you can detach the build chamber from your vacuum chamber, so that you can move your build away from the machine, process it, remove the powder and the parts, and in parallel use a second build chamber so that you have reduced downtime of your machine. Put into numbers, we have a build volume of 850 to 850, the area, and a build height of up to 1 meter. We can reach build rates of up to 1,000 cubic centimeters per hour, which pretty much competes with laser beam systems having 16 to 25 lasers operating in parallel. And what's more is that we can use the whole particle size range between 0 and 150 without having any disadvantages when applying the powder. So we are not confined to the typical powder particle size ranges, like for laser beam melting between 20 to 40 microns, or electron beam melting, which is usually found between 40 or 50 to 100 microns. And this makes it economically viable to open up a whole new field of applications. One of those I will show you in a couple of slides. First, of course, you can do standard additive manufacturing. In this case, it's just a demonstrator, a TI-64 impeller built within 12 hours using 200 microns layer height. Typically, layers are up to 100 microns maximum. That's why we reach such a high build rate. And to put it into extremes, we also used layer thicknesses of 400 microns. This rod has been built standing 280 millimeters in height, and it took us 12 hours to build. Now the special application that that we can use our system for, this production chain we saw earlier. Usually it's this linear approach. You have between the last two, between the AM system and the final part, you can recycle the powder and reuse it again for upcoming processes. But most of the powder after powder atomization is usually out of spec. So it's around the range of 60%. So you have to use the powder for either other processes or you have to recycle it in some way. And we found a means for recycling by just putting it again back into the additive manufacturing system, which is what we can do. Why? Because of the missing restriction for the powder particle size distribution. And then we produce ingots again and put it back to the Eiger atomizer and close the material circle. How does this look like? You have the powder coming into the machine. The rods that we use are hollow inside, so they are not fully molten. They have a void where at the end the loose powder, which is then sintered, is located. This is how a rod that has been molten inside an Eiger system or atomized inside an Eiger system looks like at the end with a molten tip. And inside you have this grayish area where the sintered powder is located. Exactly. And surprisingly, what we found, we designed the process in a way that we aimed at a very low loss of volatile elements when dealing with some sort of alloys, and to have a very low pickup of oxygen. And these two elements were analyzed, and surprisingly, compared to the virgin powder that came in and the recycled powder that has gone through the additive manufacturing process and atomized again, we have hardly any losses in volatile elements. This is Ti64. And the pickup of oxygen is also surprisingly low. For this, we have a means of a true recycling without having a downgraded powder at the end. To wrap this up, with the eBuild 850, we have a machine with the largest build volume currently available for powder bed fusion using an electron beam, having a build volume of 850, and 1 meter in height. We reach high build rates of up to 1,000 cubic centimeters per hour, which makes it possible, for example, to do powder recycling, of course, in combination with an Eiger system to have some sort of circular economy approach. Thank you very much for your attention.
Thank you, Alex. Our next speaker is Thomas Klein, Senior Scientist, LKR Light Metals Technologies, AIT, Austrian Institute of Technology, and his topic will be processing of Ti64 by cold metal transfer, microstructure evolution, and mechanical properties.
Thanks for the introduction, and welcome everyone to my talk. I have to say I feel a little bit exotic in this session. Everyone talking about wires, about powders, I will be talking about wires. And I hope you understand why we prefer wires against powders at the end of my talk. To introduce a little bit, we, as the Austrian Institute of Technology, have started with wire-based additive manufacturing roughly 6 or 7 years ago. And this, what I'm presenting today, is a collaborative effort together with the UNSW in Sydney. I will start with a little introduction and motivation to the process to give you a little feeling what the process is capable of. Then I will continue with the results and give you at last some conclusions and an outlook. Introduction. Why are we dealing with this process? The additive manufacturing process is growing at the moment. It is continuing to grow, and in dark violet you can see titanium, and the titanium market in this field is suggested to grow for at least for the next decade. Let's look at the process considerations. On the left-hand side, you see a comparison of different additive manufacturing processes. I would like to draw your attention to the green line. The green line refers to the wire-based additive manufacturing processes and outlines the strengths of this process. It's build rates, it's large parts, it's whereas the powder-based processes on the other side, their strengths are in complexity and very fine features. Some examples on the right-hand side, where you can see that such structures that are typically manufactured by machining can be built up on with the wire on substrates. We have here 3 examples. Typically, if possible, we prefer to include the build plate into the final product, which helps us in terms of efficiency. So you see here, for example, the build plate being part of the final structure. Of course, the process has some shortcomings, and they are mainly found in the microstructure. Best seen on the right-hand side here. This is standard titanium 6-4 after the additive process. No heat treatment and no additional elements included. You have a very coarse-grained microstructure that typically is also textured and results in anisotropic mechanical properties. Options to overcome these shortcomings are variations of the process parameters that can help you to reduce the grain size. Alloying element additions, that is exemplarily shown here. Yttrium, for example, can result in grain refinement. And the third option is interpass deformation that can be rolling or peening, which is very effective in terms of grain refinement. But if you have to incorporate that into your process, it will also give you some limitations in terms of the complexity of the part that can be built. For this talk, I will focus on the first part, so variation of processing parameters. And for this, I will start with showing you how the process we are using actually works. Very simplified on the left-hand side, we are using a current source that is connected to a torch system. We use software-based control of this torch to build up 3-dimensional objects. In this variant of the process, it's called cold metal transfer, that is shown here, the sequence. It's using a consumable electrode where the arc is ignited between the electrode and the substrate. Here you can see the burning arc. That arc forms a droplet on the tip of the wire. Once this is formed, the wire moves forward and deposits this droplet into the melt pool. When this is happening, a short circuit is formed, and only once the wire is retracted, the arc reignites and the process starts anew. This sequence happens with 70 Hertz. So this is the way we are building up structures. Of course, we have to have a system to handle the torch. These are the two operating systems we're using. One ABB robot, one KUKA robot. And they allow us to build up complex structures with light metals. What is not shown here is, of course, for titanium, we have to have an enclosure to avoid oxidation. We have developed a chamber that is suitable for the robotic system, and that is currently turned into a product by one of our partners. All right, let's come to some results. Just a quick overview. This is a photograph of such a structure built up on a substrate. You can see some black residue on the surface. That is a result of slight aluminum burn-off. You wouldn't see that in aluminum-free alloys. On the right-hand side, you see overview images of the microstructure. As you can see, it's dominated by coarse grains, coarse primary grains, and you can see the layered structure. So this is the layer height of the process in the range of 5 millimeters. So we are building up really, really fast with comparably thick layers. Some more details of the microstructure. The layer formation that I've shown before has been analyzed. And what you see is, let's start with the layers that is below here. We have on the one hand side a variation of the lath shape. And on the other hand, we have variation of the beta phase fraction. That is very locally because there the solidification conditions are kind of different. The second part is the grain structure that you can see here in comparison to the substrate. Of course, the substrate is a wrought material with a very fine grain structure. And what we see here is that throughout the build height, the primary grain structure gets slightly refined. That is an effect of heating up the material and thereby affecting the thermal gradient. A further interesting result is the local variation in chemical composition. And if you think about the material being separated into a top section and in a lower section, this is compared here. And the lower portion of the material encounters this repetitive heat treatment, whereas the topmost layer does not. It's just once deposited. So what is seen here is that it occurs segregation due to the solidification. But throughout the process and the repetitive reheating of the material, this segregation gets less and less. Now we will come to some mechanical properties of the material. What is shown here is a hardness map that shows some variations. These variations range from about 300 HV to above 400. And this is simply a result of the strong orientation dependence of the material. The overall tensile properties are shown below here. We gain very good strength properties that are comparable to wrought material. The shortcoming is the fracture strain that is slightly below 10% still, but it can be improved by subsequent heat treatment. Okay, finally, I will like to show you some of an ongoing study. We're looking at fatigue properties of the material. And if you take a look at the graph on the left-hand side, here there were samples extracted in different orientations of the build. And you don't see a pronounced trend, which is good because there is no anisotropy in terms of fatigue properties. What is interesting to note is the fracture surface. This one, it corresponds to the spot over here. So it has quite long cycle duration, but effectively it had a pore close to the surface with above 200 micrometers diameter. And if you look at the next one, this had a lifetime like 1/5 of the other at the same stress level. And the defect that we found was 1/10 in size. So this is quite surprising at first, but if you look in detail, you can see that the pore that initiated the crack was located at a prior beta grain boundary. And this is something that can happen, shouldn't, but in statistics, it can, of course, and this is why this sample failed earlier than the other. Finally, some conclusions, and I will start with the lowest one. I hope I could show you that cold metal transfer is capable of producing structures from titanium alloys, titanium 6-4 in the present study. The anisotropy is weak, but should be improved. And particularly, we should be looking at fracture strain properties. Specifically, cold metal transfer is capable of breaking epitaxially grown grains in comparison to, for example, plasma-based processes. And we have used a number of microstructural as well as mechanical characterization tools to better understand the microstructure and properties of the material. Yes, I would like to thank the Federal Ministry for funding this research. It is co-funded by industry. We're running this project together with 26 partners, which I can tell you is a challenge for coordination. But it's also giving us some very good results. Thank you very much, and I will be around for questions.
Thank you, Thomas. Our next speaker, Amir Abid, is Director of Powder Products and New Product Development with Retech Systems, LLC. And his topic will be recycling of titanium scrap to produce high-quality AM powder using plasma.
Thanks, Dave. Hello, everyone. Welcome. And thanks for sticking to the end. We're almost there. So excited to be here to talk about some of the interesting things that we at Retech are looking at to support the titanium industry and reactive and refractory metal powder. So the topic today will be looking at how do we look at production of titanium powder holistically so that we can bring the overall costs down. There is a lot of opportunity for us to use titanium and refractory powders, but some of the barriers to entry are cost, quality, and so we'll try to address some of those. Of course, it's a team effort, and hopefully we can make a small contribution to that effort. So before I go into the bulk of my talk, let me give you a little bit of an overview of who we are. So Retech has been in the industry for about 60 years. We just celebrated our 60th anniversary last year. And we're really excited to be part of this industry. I think the aerospace industry at large really innovates and contributes to technology advancement in a meaningful way. And so we're happy to be part of this journey. Our mission is to create innovative products for our customers. That's our focus. And we want to make sure that we provide the highest value. And our vision essentially is to be a premier supplier. Over the last few days, we've seen that, yeah, the aerospace industry has seen some challenges, but there are huge opportunities for growth, and we want to be part of that. And how do we achieve this? Essentially, it's obvious, and I'll state it, it's our people. We have a team of individuals that have over thousands of hours or thousands of years of experience collectively. And so we're happy to have that support from our team. And so in terms of the products that Retech produces, if you're not familiar with us, we're predominantly a vacuum and controlled atmosphere melting equipment supplier. And so we supply the titanium industry predominantly and other industries as well, medical, defense, consumer electronics, etc. And the products that we supply are vacuum arc remelting, plasma arc melting, and E-beam, which is very familiar to this industry, as well as vacuum induction melting and powder systems. And the way we kind of structure our philosophy here is that we have a deep knowledge in melting and casting. And so we want to take that knowledge base and then apply it to the powder products that we supply. And so what's the problem statement? As I mentioned at the beginning, there's an opportunity for us to increase the usage of titanium powder across the industry. And I'm happy to see some of our colleagues here on the panel talk about that already. One of the ways we can increase our usage is to, of course, drive the costs down. In addition, we have to maintain or improve the quality. Some of it's particle size distribution related, some of it's oxygen, but we really need to understand how we can control and improve the quality of the powder so that we can make really high quality parts for demanding applications. And then sustainability, the talk right before us really highlighted the need for reducing CO2 emissions and being able to control the total input of energy to producing a net part from raw material. And so one of the ways we think we can address all of these challenges is with a powder atomizer and powder consolidator system that allows us to produce a circular process. So very brief overview of powders. Essentially, the way we make powders is using high energy to take bulk and making it into finer material. And there are a variety of different ways. Gas atomization, in the powder metallurgy business, water atomization is maybe 80–90% of the processing modality. Centrifugal atomization, crushing and spheritization, a few others. But for today's talk, we'll stay with the gas atomization because in titanium, we need to have an inert environment to allow for the high purity requirements and high flow and high packing as well for the powder. Some of the areas that we want to look at as we start developing atomization systems is what are some of the drivers for AM or other advanced manufacturing methods? I mentioned sphericity. Particle sphericity is critical in additive manufacturing and metal injection molding and some other advanced manufacturing methods. But in addition to that, we need to be able to produce powders at a certain rate so that we can do production quantities. And so gas atomization seems to be the most suitable way for titanium powder for advanced manufacturing. And so the way we address the issue of how do we bring the costs down, maintain quality, and then have a circular solution for process is a system we call plasma gas atomization. Initially, I mentioned that we're leaders in melting technologies. We want to leverage that to be able to produce a production scale atomizer for titanium. And the process essentially allows us to take low-cost feed, for example, scrap or revert material for titanium, introduce it into a cold hearth to minimize oxygen and ceramic contamination, and then take molten metal and process that through a gas dye. And the gas dye has capabilities of tuning the particle size distribution so we can produce a broad range of particle sizes for different additive manufacturing methods. And so if I just compare these technologies to what I would call the state of the art for producing titanium, such as wire atomization or electrode atomization and vacuum induction melting, the PGA system allows us to use raw material feedstock in a broad configuration. So we can really bring the costs down. If we use scrap or yesterday's talk, there was a description that about 95% of the CO2 input is lower for scrap versus raw sponge and master alloy. So it's really exciting to be able to use low-cost feed. In addition to that, because we have plasma melting, we can really enhance the throughput on these systems. Traditionally, for making titanium ingot and bar, we use plasma at scales of thousands of kilograms an hour. And so we can then leverage that capability to then produce powder at scale. I mentioned the flexibility of producing a variety of different particle sizes using the efficient gas dye. And then overall, as you stack all of these benefits, you can then come to a lower total cost for titanium powder. Some examples of what feedstock that we could use in a plasma gas atomizer are machine turnings, cuttings and trimmings from plate, and some small scrap parts from additive manufacturing builds. So it gives you a lot of flexibility to use a variety of different feedstock. So overall, the benefits of the PGA are that we can use PAM technology, which is a mature melting technology, to produce reactive and refractory alloys, including titanium. The process is inherently scalable, which is critical for us to then take the powder solutions to a production scale. Overall, we are able to control the costs by improving the feedstock requirements, the ability to control particle size distribution, which is critical. And then ability to melt in a plasma system opens up the types of alloys you can produce. Because of the flexibility of feed, you don't have to pre-alloy your feedstock, which allows you to then use complex feedstocks to pre-alloy, to alloy in situ in the hearth. So we talked about PGA. I'm going to switch gears for just a minute and say, okay, now that we have a solution to produce powder, what next? As Alex mentioned earlier, most atomization systems use high energy to break apart bulk liquid feeds input. And so you inherently have a distribution of particles. On the image here on the right, you'll see that there's a distribution where a portion of that gets used in additive manufacturing or metal injection molding or hot isostatic press. You always have some amount of over and undersize that you have to account for. And so if you can take the out of spec powder and take it back and use the high quality that you already have with the powder and bring it back into a solid form, there's value there. So we've developed a system called a powder consolidator that takes oversized powder and then reintroduces it into a melt and produces ingot. The typical sizes of these ingots can be anywhere from 2-inch to 10-inch. And these are some examples of Ti-6-4 oversized powder that was consolidated to form ingots. You can see that the surface finish is fairly decent. And when we did the chemistry on these and the density of these powders, ingots were very good, very close to what was the input powder. And I'll emphasize that, everything that we do at Retech focuses on trying to make sure that we can scale. Because that's what our customers are demanding. And so this consolidator system has the capability of scaling all the way from 50 tons to about 500 tons a year. So the ability to take oversized powder, which has very high purity, and bring it back into a high value product like a bar that can then be used to produce powder or convert into wire or even being used as the mill product is very, very interesting. The quality of the ingots produced are fairly high, so that can be used with minimal additional processing for other downstream high value products. And we'll continue to look at various other alloys that we can consolidate using this process. And so, if I were to wrap the talk up into overall summary, the PGA, the consolidator, allows us to create a holistic cyclical process where we take low-cost feed, we introduce that feed into a plasma hearth melt that has a fairly high melt rate, then produce powders at scale, and then taking that powder, printing with it or using it in other applications like MIM or HIP, and then taking any oversized powder from that process, putting it back right into the recycled stream, consolidating it, and then taking oversized powder or ingot, in this case, back into the atomizer allows us to really have that flexibility and closed loop, minimize our overall cost of the process, decrease the energy consumption, and hopefully increase the adoption of titanium powder across our industry. With that, I'll close my talk, and if there are any questions, I guess we can take it after. I'll keep my slide up for my contact information.
Thank you, Amir. Last but not least is Carl Bollert, professor, Michigan State University, and his topic will be characterization of the microstructure, tensile, fatigue, and creep behavior of powder metallurgy process rolled and extruded Ti 641B alloys.
Well, first of all, thank you all for sticking around to listen to the very last talk of the conference. And what I really want to thank is the International Titanium Association, especially Jennifer Simpson, for helping myself and 20 students from the US who are scattered throughout the room to help attend this conference. We're having a great time, and especially the students. So what I like to talk about is some boron modified titanium technology that's been relatively mature and used since 2000. And some of the research that we've done on it at Michigan State University, mostly done by Wei Chen, who is now at Beijing Aerospace Technology in Beijing. And as we know, we've heard already from this morning, it's used quite a bit in the titanium industry. And why is titanium used? Weight reduction, creep resistance, fatigue resistance. And what we're trying to get at is how we can modify titanium with alloying additions. And boron is a famous inoculant, which reduces the grain size, especially in castings and other processing of titanium alloys. And so we're taking advantage of that so we don't have to go through as much raw processing to get the strength of titanium increased and the stiffness increased by adding small amounts of boron. And really, this was the grandfather of boron modified titanium is Professor Sato, or Dr. Sato in Japan, who really pushed forward this technique in the early 2000s so that it's in the automotive industry for sure. And it's in the Altetha. It's as a intake and exhaust valve for that. And what he started with was blended elemental powder metallurgy process for manufacturing these engine valves. And he kind of walked through the blended elemental technique with these powders. Then we mixed them, compact them, vacuum sintered, traditional powder metallurgy technology, made it into a billet, then hot worked it, heat treated, and machine coated it. And it's offered significant savings in terms of performance based on stiffness, strength, and weight. And that's one of the success stories for this boron modified titanium technology. Now, adding boron can be done in a variety of processing techniques, whether it's casting, whether it's powder metallurgy, and powder metallurgy in the form of pre-alloyed powder or blended elemental powder like we had in the last slide. And in each of those cases, we can go through the processing techniques that are traditional for physical metallurgy, and we're ending up with a raw product that will be significant advantages to it. Higher specific stiffness. By only adding 1 weight percent boron, we can get up to 15% stiffness increase in strength, and up to 50% or higher than that for most other titanium alloys. And the trick is this: because it's an inoculant, when you put it in a casting and you cast it, you can get significantly reduced grain size on the orders of magnitude smaller than you would without the 1% or 0.1% boron. The trick is to add in the amount of boron that you want in the material for the performance that you want. The more boron you put in there, the more the ductility will decrease, but you get higher strength and higher stiffness. So there's a variety of different applications that this can be used for. It's going to not decrease the weight too much. We know boron's lighter weight, and it's not going to increase the cost too much. But what it does do is if you start with a smaller size grain size in your casting, then you don't need to go to as much raw processing, or even can avoid raw processing in your material. And that will be a significant amount of cost savings. So in this work that we did, Wei Chen evaluated a bunch of different compositions and different processing techniques. And a couple of those were based on powder metallurgy. And he wanted to understand the processing effects on the elevated temperature, fatigue, and creep behavior to see if we could use this at elevated temperatures. And then to also evaluate the amount of boron that could be used to evaluate what the optimal content would be for the elevated temperature, creep, and fatigue behavior. And we looked at, in particular, powder metallurgy rolled plate versus powder metallurgy extrusions, and we're going to compare that to cast material. And here's on the left is powder metallurgy rolled Ti-64 with 1 boron, and on the right is powder metallurgy extruded Ti-64 with 1 boron, and the 1 boron is by weight percent. So we've seen a lot of talks about processing, and this is no significant difference in that. This is the rolled. We typically have a rolled billet. We go through rollings, and we can reduce it without seeing much cracking at all. And same thing with extrusions. And we're going to talk about differences in the texture that were caused from the rolling versus the extrusion, where the extrusion resulted in a significant change in the texture compared to the rolled material. And here's a picture of the microstructures. Again, on the left is the 641 boron with the rolled, and this is on the right. And it was rolled in this, it was extruded in this direction and rolled in this direction. But you can see that there's a strong difference in the microstructures. In these backscattered images, the black is the titanium borides, as the boron tends to form TiB or TiB2. In this case, it's TiB. And they are significantly aligned in the extrusion with respect to the extrusion axis. But that wasn't the case in the rolled plate. And in addition, we can have texture within the matrix, which is the alpha beta matrix. And we found out that there's, for the same magnification, you can see a much finer alpha grain size on the order of 3.6 microns, and it's double or higher in the rolled condition. And if we look back, the temperatures were relatively consistent between the two, up to 1200 degrees C for the processing. So that may have an effect on the grain size, but for sure that we get this significantly happening, whether we have 0.1 boron or 1 boron, we get whiskers that are aligned with the extrusion direction. And this, we're going to find out later, is the stiffest direction for the titanium boride phase, which results in even higher stiffening than when you have a random oriented whisker. And roughly the volume fraction is the same of the titanium boride phase in both microstructures. So if we look at this texture, we can look at it in a few ways, from EBSD or from X-ray diffraction. And this is the PM rolled in the longitudinal direction, and the transverse in the rolled face. And we didn't see a very, very, very strong texture develop in this material. If you look at the extruded, though, both the alpha phase was strongly textured, and we already see the morphology of the titanium boride whiskers. Well, the alpha phase titanium, this is an inverse pole figure from EBSD, And it was strongly textured with the basal plane perpendicular to the extrusion direction. And that has implications on the slip systems and the ductility that would come out of that. And if you look at the titanium boride phase, we know that it was strongly textured with their line direction with respect to the extrusion direction. And that was the 020 is the growth direction of the TIB phase. Well, if this is a basal slip would be prevented if it was perpendicular to extrusion direction in the extrusion direction if we did a tensile test in that direction. So that would mean that we'd have limited ductility and perhaps higher strength. And we know this because of the literature. At elevated temperature, we can get A and C plus A slip in the alpha phase, where C plus A slip tends to be more difficult. We look at this with increased temperature, the critical resolve shear stress decreases for all the slip systems. It decreases significantly even for the C plus A slip. And the alpha basal plane, when it's oriented perpendicular to the extrusion axis, A slip is not possible. Therefore, we could have a reduction in the elongation of failure. And so after the transformation, it would be expected that the 002 basal plane is oriented 0 or 90 degrees to the extrusion action. And this would result in what we call a hard orientation, something that would be highly strength, but may not be the best in terms of ductility. So when we look at this now, and we look at on the left is elevated temperature tensile tests for materials that are cast, and then CE stands for cast and extruded. And we have no boron, 0.1 boron, and then we have 1 weight % boron. And first of all, the as cast material, in the cast and extruded material right there, has the lowest ductility. And so that is because of this orientation effect, the texturing effect of the alpha phase, and as well as the highly textured TIB phase. And what we see at the top here is that we can get cast and extruded with 1 boron to have strengths on the order of 800 degrees C at 455 degrees, or 800 megapascals at 455 degrees C. And it's relatively ductile, 10% elongation. If we look at just the cast and extruded without boron, we get a slightly lower strength. With 0.1 boron, we gain a little bit more strength. And so we're gaining strength as we add more boron, and the highest amount of boron results in the least amount of elongation, but we're still getting 10% elongation in this particular case. So we certainly get major advantages by adding boron in the cast and extruded state. And now if we look over here, we have all these are now 455 degrees C tensile tests. They all contain 1 boron, and we're going to compare the rolled in red versus the extruded. And the extruded, which we had that strong texture in, had a much higher tensile strength, again on the order of the cast and extruded with the powder metallurgy extruded. And we had elongations, again, on the order of the same amount as that for the cast and extruded one right there, which is the same property as the green over here. And if we look at just the as cast, again, that was the one with the least amount of elongation without, with the 1 boron. And then the powder metallurgy rolled doesn't quite reach the same strengths as the powder metallurgy extruded. Again, probably because of the texturing effect. If we look in terms of stiffness, the more boron we add, the higher the stiffness, where we can obtain Young's modulus values on the order of 117 megapascals or 113 megapascals, whereas the 6,4 without any boron is going to be on the order of 90. So we're gaining roughly 20% stiffness by adding in the boron. If we look at the tensile tests, we've done a lot of experiments in situ to evaluate the damage progression in the materials, and we find out that as to no surprise, that this TIB is a reinforcing phase. It's very hard and very strong, and therefore it's taking on the load from the matrix. As it takes on the load from the matrix, then it tends to develop the cracks first in the material, and we can see the cracking that happens throughout the titanium boride. Eventually, when the titanium boride cracks enough, then it'll shed load back to the matrix, and then it'll cause failure in the part. If we look in the fatigue behavior, that was a big question for aerospace. We get improvements in stiffness, we get improvements in tensile strength without too much of a debit in the elongation of failure. But what's going to happen in fatigue with these titanium borides? Is it going to be able to fly? So we did a lot of testing at 455 degrees C, tensile type of testing with an R stress ratio of 0.1, meaning we never went into compression, 5 hertz frequency, 2 repeats per condition. And before we started the test, we had this type of information for titanium alloys that typically wrought titanium alloys are going to be orders of magnitude higher in creep or fatigue life at the same stress level than cast materials, where powders would sit somewhere in between. So how would this translate? By adding in boron. On the left-hand side, we have fatigue temperatures, tension again, just like the tension tests, but it's 455 degrees C, and we're looking at cycles to failure versus maximum applied stress. And there's some interesting features. First of all, the as cast had the lowest fatigue threshold stress, and the highest one was the powder metallurgy extruded, which was on the same as the powder or the cast and extruded 641 boron. So it turns out that we didn't get a debit in terms of comparison by this PM extruded material in depth in fatigue life at 455 degrees C, and the PM rolled, which also was subpar performance in tensile testing at 455 degrees C, had a slight debit in the fatigue lives versus the PM rolled material. Of course, we could do more tests, but this is a good indication that we have higher fatigue threshold stresses in the PM rolled. This is, again, just a repeat of the tensile tests. So it looks like this PM extruded material would be the optimal material in terms of if you want the highest stiffness and highest mechanical performance. And one of the things that we could look at in terms of the processing, in terms of the deformation behavior, was how are the dislocations going to build up within the microstructure? Well, we know that titanium whiskers impede dislocation motion. They have an orthorhombic structure. They don't have many slip systems. And we've seen buildup at titanium boride whiskers in terms of the dislocations that are trapped in them. And we've also looked at dislocation structures, and they typically are forming and confined within the alpha beta phase and confined between these whiskers. And reducing the as cast grain size can help reduce the dislocation slip length, reducing the stress concentrations, reducing the ability to crack. That's a good thing in terms of fatigue or tension. And I'm glad that Thomas Klein showed some fracture surfaces and fatigue earlier. We have very similar features, whether you add boron or don't add boron in Ti-6-4 compared to his wire AM materials. And so the cracks, as we saw in tension, typically initiated at whiskers, and they were typically close to the fracture surface, but we still could get ductile type of failure away from the crack initiation site. And we did see some fatigue striations. There wasn't anything too surprising in this, but it wasn't terrible. That initiation was always something that was a detrimental effect at the titanium whiskers. In terms of the creep behavior, again, we looked at 455 degrees C, and we looked at 400 megapascals for our applied stress in this case, and 450 in this particular case. And these are just one-off tests. We did a bunch of tests, but I want to show you these representative ones. The first one is the cast and extruded. That one had the best creep resistance. Then it was followed by the PM rolled. And it turned out in this particular case for creep, the PM extruded material had a higher creep rate and a lower creep resistance than the cast and extruded, all for the 641 boron concentration. So it looks like the extruded material in the powder metallurgy is going to be worse in creep than the cast and extruded or the rolled and extruded material. And that was also true if you look at it to a slightly higher stress 450 MPa. There was a slight shift in the extrusion versus the rolling in this particular case. We've done a bunch of tests to identify what the activation energies were, tried understanding the deformation mechanisms, and publish that in different articles. But it's improved by the addition of the lenticular alpha phase. We know that from past research, and therefore that's an important component to control the alpha morphology. But if we look at in terms of the fatigue properties, we were measuring during the fatigue tests the strain, and it was at 455 degrees C. We could have a Duell during different parts of the fatigue test. And during that dwell, we can identify, because we are measuring the strain over a function of time. And so this is strain versus time during the fatigue test, and it looks just like a creep test. And these are different amounts of applied load in the fatigue test. And we can try to identify from this what's going on. We basically know that there's some ratcheting going on in the material. And if we look at, this is a PM extruded, we know that it's going to ratchet just like creep and have a function of creep at the certain conditions. We can measure this ratcheting rate and apply it for both of these conditions and try to mimic and model what's going on in terms of the fatigue, in terms of the creep behavior, to understand why we're not getting the best performance in the PM extruded material. And so to conclude, that processing significantly influenced the fatigue behavior of Ti-6.4, where the PM processing induced what we call an equiax grain size that results in enhanced fatigue lives compared to the cast metallurgy. The finest equiax microstructure resulted in the greatest fatigue lives. And the texture induced through the extrusions enhanced the tensile and fatigue strengths by aligning the alpha phase and the TIB phase in what's called hard orientations that we're not going to see slip happening as much in. The extruded alloys exhibited tensile anisotropy, where the extrusion actions were stronger than the transverse orientations, and they were also less ductile than the transverse orientations. And overall, I think that this is still an important technology that hasn't reached its fruition. By adding boron into titanium, we can process it in the same way as conventional titanium, and we can get enhancements in the properties. And so I think it still has potential use. And with that, I'd like to show some of the acknowledgements. This was mostly done with our collaborators at Air Force Research Lab and some of the people at Oak Ridge National Lab that help us with some of this characterization. Thank you very much.
So I just want to thank our panel speakers.